A lunar month is exactly the cycle of one moon rotation.
28 days. Oh, okay.
And a fortnight is 2 weeks or 14 days, so it's from full to gone to full time, and then back up to like.
Yeah, but to make it line up with the actual, of the actual cycle of the Earth going around the Sun. So every so often there's an extra month in a year in the lunar calendar to match up with that. Yeah. So it's kind of odd. Instead of leap day, we have a leap month. But we have to accumulate a leap month, from many years, because you only take 4 years to save up for one leap day. But in order to save up for one leap month, it takes longer. So it's kind of odd. But you can look up a lunar calendar app or something. You can actually figure out what day it is today and stuff like that. All right. So what we'll do today is going to be a homework assignment. I have a new homework assignment on Moodle that is not for you. As I know what you guys are thinking. It's like, oh no, we have that one on Thursday, and we have a new homework assignment. No, this one is for myself. Yes. But by doing this homework assignment in class, I'm hoping that I'll be able to show you guys what you need to do for your own homework assignment. So that's the plan for today. All right. So are there any questions other than who sent me messages? No? So I'm going to ignore for the time being and get started with today's lecture. The recorder is on. Let me just double check, make sure that I am recording. Okay, it is recording. Okay, and get rid of Firefox. All right, so this is cisp310, and you cannot find this homework assignment. If you want to, I can make it visible, but I don't want to make it visible until I have a chance to tell you guys what I'm doing with it, so that people do not accidentally take it as a new homework assignment and try to do it. Not that I mind people doing it, but I don't want people to kind of put time into this one when they barely have enough time for the other one. Okay. Because I got some questions about your actual homework assignment, which is Microcoding 1. So what I did was I created a new homework assignment for myself, which is Microcoding 1 for TAC, which means you don't do this one. This is just an example of what to do. Okay? The format is very similar to the one that you have to do, except I implement some different instructions. Okay? So I think this would be a good parallel to what you have to do for your own homework assignment. And we're going to get started with the same files. So today's class is going to be quite useful for those of you who are kind of have not started yet. Okay. Any questions before I get started with Logit? Because most of what we're going to do today is in Logit and also the spreadsheet. Okay, kind of the stuff that we did last time. But I'm hoping that this will give you an idea of the workflow. Okay, not just the tools, not just the concepts, but the workflow of how to get your homework assignment done. Any questions before we get started? Okay, no questions. So I'm hoping this will answer most of the questions. And it's Logit Sim. And there we go. So I'll go ahead and get this started. There we go. So you're not going to change the processor itself, except for those of you who want to kind of like, okay, I don't want the RAM module to reset whenever we click the actual reset button. What you can do is to sever this connection of clear, so that when you reset the main reset line, it doesn't trigger the RAM module to also reset. Okay, so to disconnect that one is pretty easy. All you have to do is to select this connection here and just delete it. Okay, so that's one thing you can do to kind of make sure that you don't accidentally remove or change or clear the content of the RAM when you're just testing your program. Okay, so are there any questions about this step? I'll show you exactly where it goes here.
It's pretty connected.
The reset line?
Yeah.
Yeah, the reset line itself is really connected, but you can just change this one.
It seems to unnecessarily go all the way around when the line right to the OR
is
Uh-huh.
also the reset line.
Oh, you mean this one
Yeah.
here? Yep, that is true. You can see, how components were added, at a different stage, and I just go like, okay. All right. So this is the one that you can, remove. Do not remove the entire reset line. We still need that. It's just that this segment can be removed first, just so that we don't accidentally, clear the content of memory. So I'm going to remove it just like this. And now, when I hit the reset button, the RAM content is not going to change. Okay. Any questions at this point? No questions? Okay. So if there are no questions about this, we're going to change the file names. So we'll right-click on this one, and then we'll say save image into a different file name, because when you turn in your homework assignment, this has to be solution.rom, R-O-M, and click save. And this one has to be solution.ram. So save image. This is solution.ram. All right. So now that I have saved the basic setup, it's time to take a look at the homework assignment and figure out what instructions I'm supposed to do or supposed to implement. Okay. So we're switching back to the browser. The format of my homework assignment, which is not something that you have to do, I want to re-emphasize in case someone walks in late and go like, oh no, we have a new homework assignment. Well, you guys can tell that person that it's actually a new homework assignment, but that's up to you. So what I'm going to do is I will use the opcode 0110XXYY, which is in binary. Each position is 1 bit, to implement a compare instruction. Not a subtraction, so I don't want to do your homework assignment entirely. So this is just a compare instruction. And the compare instruction is different from a subtraction instruction in that it does not store the result. Okay? It will go through the whole gyration of subtracting, but it does not store the result. So the result would be calculated out of the ALU, and then it will just be forgotten. Okay? Yep.
What's the point of the compare if we're not storing the result?
We are going to use this instruction later on, because it will still be used to change the flags. Okay, so we are not quite at the point where we have the 0 flag, the carry flag, and whatnot that are actually stored individually.
Okay.
So at this point, it doesn't seem to make any sense. But later on, we'll expand the architecture itself to be able to store those flags, because right now the architecture itself does not store the flags.
Okay, and so comparing is what will give us those flags later on. The compare instruction will give us the flags later on, is what you're saying.
Correct.
Okay.
Yep. I'm just hearing it.
There is a cricket.
Yeah.
Oh, there is? Okay. So this room has a bug.
Yes, that's right.
And you know what my job is, right?
Debugging.
Debug it. And next time I'm going to bring this in, as long as the campus police is okay with this. It's called bug assault.
Bug assault?
Yeah, it's fun.
Oh, I've actually seen this on the science channel. Good.
Yeah, this is bug assault. It's basically a shotgun that's based on an air gun. You load it up with like table salt, nothing fancy, and you have to pump it, so it pumps like a shotgun. Even has a safety and a sight, and then it just shoots out a little grain of little patch of salt at really low velocity, but it's enough to kill like flies. I tried it on various pests. It's only good on flies and mosquitoes. It will only do one thing to yellow jackets. Make them mad. But it doesn't do a single thing actually to yellow jackets. It just kind of piss them off. It will take about 7 shots to kill a black widow. The good thing about black widow is they're slow moving, so I actually have time to shoot them like 7 times. I would suspect this is effective as well on slugs.
Probably a lot less.
Yeah, kind of. But that would be kind of cruel on slugs. Yeah. Yep. Exactly. There has to be some kind of interspecies convention of some kind. Yeah. So anyway, when I bought it, it was not this expensive. It was a lot less expensive, but it's kind of cool. I tried it myself, to see how what kind of power it has. So I first used a piece of paper, right? Point blank, shoot a piece of paper. Could not even penetrate a normal piece of paper. If you have paper towel, yeah, it would kind of make a little hole, and then I tested it on myself, and it's a little stain, kind of no more than like a rubber band. If I use a rubber band and kind of like snap it on my own skin, that's kind of the sensation of this gun on human skin.
Did you ever season your steak with it?
Sorry?
Did you ever season your steak with it?
I think it can take on like larger grains of salt, and it would probably do something more to Yellow Jackets.
That's salt that you grind.
Huh?
Get the salt that you have to grind up
Yeah.
and just stick it in there.
Yep. Okay, that's a digression. Okay, so getting back to the subtraction instruction. All right, so the first question is, what is this, actually telling us, and how do we relay this to the microcode? Okay, so this is the part of the microcode. In other words, this particular instruction that we will store in RAM is going to correspond to 0110 0000 in binary as the start location in ROM, in the microcode ROM. Okay, so I will talk about that later. And also, if you look at this as a binary number, 0110, what is that in hexadecimal, in base 16? 6, right? Okay, so that means the start address in ROM corresponding to this instruction is 60. Are we doing okay so far?
Why is the XXYY 00?
The XXYY are corresponding to the registers, because you have to specify 2 registers for the comparison.
Okay.
So those are, so XX specifies one register and YY specifies the other register.
And we're assuming they're going to start off as 00 for both of them, right? Because you said 0110 0000. You said it was 4 zeros at the end of that.
No, the instruction is split into 2 parts, right? When you look at each instruction that you store in RAM, okay, there are 2 parts to it. This part is going to help you index into the microcode page to start the actual microcode specification. This part here specifies which registers is being used by this specific instruction.
Okay.
So the pattern is 0110 and then blah 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 blah. Okay. To index into the microcode page, you don't need the blah 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 blah. But to actually execute the instruction, you need to know for that particular instruction which registers are being used.
Okay.
That
makes sense.
okay?
No, that makes sense.
All right, so I'm going to read the rest of this. I'm using the same format as your homework assignment here. To do this, I recommend the following steps. Examine the processor design and find out how registers out of the register bank are connected to the ALU, because you need to figure out which number is being subtracted from which other number. And at this point, this instruction only needs to output the result of the subtraction, but it does not need to store the result back into the register bank, because that would turn it into a subtraction instruction and not a compare instruction. So a compare instruction is the same as a subtract instruction, except it does not store the result. Okay. All right, so are there any questions about the description of this particular instruction? That's the entire description of this opcode. No questions? Okay. So if there are no questions about this, we'll go ahead and try to figure out, okay, what components of the processor architecture will be involved in this case, and how exactly are we going to control those components. So we'll take a quick look at Logit Sim first, okay? And the good thing about this instruction is we only have to look at a very small part of the processor, because we don't need to look into RAM or the indirect register or anything like that. Everything that we need is kind of here already. Okay, so we just need to look at this portion of the processor, and I think I can zoom in one more time, and there will still be enough space to look at everything. There we go. Okay, this is our register bank, and this is our ALU. So these two are definitely connected, and we want to figure out how they're connected. So if you hover over a particular connection, it tells you what it is. So register 0, okay, if you click on it, it will show you how it's connected. Is connected to D in 0. Okay, so you might want to take note of this, okay, because when you're writing the instruction, you
Bless
kind of
you.
need to know these two. So register out 0 from the register bank goes to D in 0 of the ALU. So that makes the other one, which is this one here, the other output, which is register out 1 going into D in 1. Okay, so register out 1 goes into D in 1. Now, for those of you who have done the add instruction already, for the homework assignment, you already know this, okay? Because you have to figure out this out in order to do your homework. Okay. So the next question is look into the ALU and find out, are we subtracting D in 1 from D in 0 or the other way around? Okay. So to do that, you can use the magnification symbol. I turn it into the hierarchical view first, and then go into the ALU and try to find out, okay, exactly how are we subtracting? So when you go to the subtractor here, you can see that one input is going to D in 0, the other one is going to D in 1, which is over here. So this is the minuend or minuend, the number from which to subtract, and this is the subtract end, which is the number to subtract from the minuend. So the I think we are subtracting this number from this number. Now, just to be sure, okay, just to be sure we can do this. Okay, we go into the simulation mode for this particular component, and we'll just go ahead and specify and say super circuit state, create a new circuit state.
You have to say okay.
Okay. So now we'll go ahead and specify the other number, and we'll say let's subtract 1 from 0. And to get to the output, you can just hover over a wire or click a wire, and it shows me it is 1. So this is already enough to tell me, which one is being subtracted from which other one, because if you subtract 1 from 0, you get 1, 1, 1, 1, 1, 1, 1, 1 with a borrow of 1. If you subtract 0 from 1, you get 1 back. Okay, so the suspicion was right. The top number is the one being subtracted from, and then the bottom one is the one that is the one that subtracts. So in this case, that means the calculation using the subtractor is D in 0 minus D in 1.
D in 1 minus D in 0.
D in, oh, right.
I think,
No, this is right.
Yeah.
The bottom one is the one that
Yeah,
is
zero's
that
the
specifies
subtract.
how much to subtract from the first one. The first one is D in 0. So this is actually correct. All right. Any questions about this? No questions? All right. So if there are no questions about this, we'll go back to the main design, which is this part here. So our job is to figure out how do we specify which register, specifies which one. How do we specify register out 0, and how do we specify register out 1? So those are the select bits into the register bank, and the select bits are specified here. Okay, so it should be clickable. So if we click on this one, it specifies both register select 0 and also the register input select, which is not useful in this case because we are not overwriting any register. But this one is, okay? That makes the other one, which is this one here, click, specify the other register. Okay. So if I want to specify this is bit 0 and bit 1 of the instruction, this is bit 2 to bit 3 of an instruction. Are we still doing okay so far? This goes here, and this goes. Okay. All right. So with this in mind, the next thing we have to do now is to figure out, okay, so what pins do we need to exercise in order to get this operation to work? And to do that, I personally would use the spreadsheet because it's helpful. At least it will list out all the control signals already. Okay, so this way it's easy to figure out. Okay, you don't have to calculate which bit is doing what. It's already documented. So that's the next thing I will do is to go to my folder and do a LibreOffice on the ODS file, which is mccstates.ods. and we already have some instructions allocated. So I just start a new one here. Okay, I'm going to delete this whole row. So we'll go ahead and just delete. We can just delete the selected row here. So I'm going to use this to implement my new instruction. And the new instruction, I'm going to document it, consistently with the rest of the instructions, because this is going to be 0, 1, 1, 0, the most significant 4 bits. So I'm going to be consistent here and say this is instruction 6, which is actually in hexadecimal 6. This is my compare instruction, and the compare instruction requires 2 registers. And at this point, I'm not really going to be too picky about which one goes first, whether we specify register 0 first or not, because I'm not writing an assembler to interpret the instructions. So as far as we know, which one goes first, that's already good enough. Okay. So first thing first, we have to specify which operation we are selecting out of the ALU. That's you have 8 choices here because there are 3 bits going into the operation selection of the ALU. What we really need is just 1 here, okay? Because we only have 2 operations that are actually implemented in the ALU. MCC clear is not needed yet, okay? We need that at the end of everything, so we'll put a 0 here. Register 1 enable, yes, we need that. Register 0 open enable, we'll need that in order to feed into the ALU. The next one is write enable. Nope, don't need that because we are not overwriting anything in the register bank. Not ever in this instruction. When you're doing add, eventually you need to turn that on. Indirect register write enable. Nope, because we are not dealing with the indirect register at all. RAM selection. Nope, because we are not using RAM at all in this case. MCC instruction load / increment. This is going to be a 0 for the time being because I'm not even ready to deal with the MCC or the microcode counter just yet. So it will be a 0 to basically specify increment instruction here. RAM address PC indirect, we'll just specify the default, which is going to be 1 because we want to use the program counter, but it's not really being exercised here anyway. This one is not used, so we don't need to specify anything. RAM read write, we are not doing anything here. We can just specify a 1. ALU output enable, yep, we kind of need that, right? Because we are going to take the output of the ALU, but we're not going to store anything, okay? So in this instruction, you don't really need to turn it into a 1, but when we have the other parts of the ALU done, this has to be enabled so that we can store the carry bit out of the ALU. Instruction register write enable. Nope, we don't need to override the instruction register. PC write enable. Nope, we don't need to do that. PC select increment. We have RAM data. We can just specify a 1, but we are not going to override the PC, the program counter anyway, so it's not going to be doing anything. So once we specify all the bits, it is time to just copy and paste these 2. So now we know the microcode, the first step to implement this instruction, the first microcode is going to be 13431 in hexadecimal. Are we doing okay so far with this? Okay. So we'll go ahead and just put this into the ROM now, okay, because we have 1 instruction. So we switch back into the Logic Sim, and this time we have to scroll our way to the ROM module, which is down here. Right click on it, specify edit content, and go to the page that is responsible. This one is starting at 60, and we'll just go ahead and type that number in. And of course I cannot remember the number, 13431. That should be a pretty easy number to remember. 13431. There we go. Are there any questions at this point about the workflow of implementing an instruction? So the instruction is an 8-bit thing that you store in RAM. But in order for an instruction to be meaningful, to actually do anything, you have to have the right microcode in the ROM in order to do all the things, to coordinate all the control signals, all the lines and whatnot. Is that okay? So if you want to use an analogy, it's kind of like the instruction that you store in RAM is the invocation of a subroutine. It's the calling of a subroutine in C and C++. But where is the definition of the subroutine? It's the microcode in the ROM. So the relationship between instruction in RAM and the microcode in the ROM is kind of like that. Okay, one is the invocation that has parameters, right? What do you think these two things are? They're parameters. Okay, but the subroutine itself, does not need to know about these two because these two are directly going into the register bank to specify, oh, who's the register out 0 from the register bank, who's going to be the register output 1 from the register bank. Yep.
How do you define when you put it 1, when you put it 0 there?
You look at the meaning of each line. I mean, there's no getting around that part. So you still have to understand the architecture itself and be able to figure out, okay, what is this line actually doing?
So 1 means they're working.
One, well, it depends on what you're specifying, right? Because in this column here, 1 means we are just selecting to increment the program counter if we say the program counter can change. A 0 means we are not incrementing. We are basically taking whatever is in the RAM data bus and putting into the program counter itself. So it means different things depending on which control signal you're dealing with.
So
All right.
ALU out and we put it 1, ALU out.
Well, then you have to figure out what it is. Okay.
So which means we have ALU output to somewhere.
Well, okay, the way you do this, you look at this number here, it is bit 13. You go to the design, and then you figure out where is bit 13 going, right? So you look at the output of the microcode. This is bit 13.
Yeah.
Okay, bit 13 is the one above that. You click it, and then you figure out where it's going. It goes into here, and it goes into here. And then you have to figure out, okay, but what does that mean? Okay, what is this signal into a mux? Okay, and what is this? What is? No, it's not. But that's for you to figure out. And you also have to figure out what is operation output enable. What does it mean in the ALU? Now, since the ALU is a component that we defined, so the way to do this is to double click on it and say, okay, what is output enable? Operation output enable. It is this pin here. It goes into this interface into the mux, which is enable. So that's what you need to do to figure out what each bit of the microcode is really doing to the processor architecture.
So if we need output here, so we need to enable, we need to put 1 there. That
Well, that you can experiment, okay, and figure out what it's going to do. All right. Any other questions? No questions? Okay. So I think I'm pretty much done with this instruction. Okay. So I will go ahead and finish up the instruction here because every instruction has to end in a certain way. If you go back to this spreadsheet here and look at all the instructions, okay, this instruction ends with a particular pattern. This instruction ends with a particular pattern. And what is common to all of these implementations is the MCC clear has to be a 1 in order for us to go back to the fetch cycle to fetch the next instruction. Okay, so that is something that you have to do regardless of which instruction you're dealing with. Unless you have no intention to go back and fetch the next instruction and just wanting to get stuck, doing the same thing over and over again. There is an instruction to do that. In most architectures, it's usually called a HALT instruction, H-A-L-T, HALT.
So it doesn't halt, it actually loops it.
Inside the microcode engine, it actually does the looping, but from the outside, it's not, since it's not fetching new instructions from RAM anymore, so it's kind of like, oh, this is not coming back, it's not returning at all. Yep.
For the fetch cycle, the first row, the hexadecimal number is like 11,500, and it's not in the microcode engine.
Oh, you mean the first one?
Yeah, the first row.
Oh, you mean this one?
Yeah, that's
The 11500?
Yeah, it's not.
Huh. Okay, we'll put it back in then. Does anyone put it back in?
No,
It doesn't seem to make a difference.
yeah, it doesn't, I just wondered why.
I think it doesn't make a difference because the second clock, already contains those exact bits. So I was just playing it safe, with putting it here. But let's put it back here. 11500. There we go. And it doesn't hurt to save this occasionally, just in case in case the tool itself crashes or anything. You don't want to like put 2 hours of work into it and then it crashes, or you have a power fail and bad things happen. All right. Okay, so getting back to the spreadsheet. Okay, one last thing to do. We have to finish up this instruction. It's already done. Okay, for the time being, this is all we want to do with the subtract instruction or the compare instruction. So we'll keep the same thing here. Okay, but we'll put a 1 into MCC clear, to clear the microcode code counter. Turn off all the registers output. Okay, because the default is we don't want to enable anything unless we really intend to do something. RAM select is going to be a 0 because the fetch cycle will turn it back on anyway by itself. Microcode instruction load / increment, we'll just put it back into a 0 because the microcode, the fetch cycle will clear this anyway. The rest we can just kind of keep it the same way as before. Doesn't matter about this one. And the reason why we specify a read operation with RAM and not a write operation is just in case you enable it, it doesn't destroy the content in RAM, but it really should not happen because it's already disabled. And we'll turn off the ALU output enabled in this case because we want to turn off output as much as we can, just so that we minimize any chances of a bus fight. Turn off this, PC write enable, turn that off. Go back to increment program counter. The fetch cycle will take care of this anyway. So you can see that now our new opcode or the new microcode is going to be 11409. Okay, and you can see it's very similar to the other one. The only difference is we are still specifying the subtraction operation out of the ALU instead of the add operation out of the ALU. That's why the least significant bit is different. Well, yeah, because the least significant 3 bits are for the ALU output specification. That's why this one is a little bit different. Okay, great. So what do we do next? Well, we just copy this number, right? 11409, and put it into the ROM code here. So we go back into the edit content and put it here. 11409, and remember to save the ROM content because I think we are done with the ROM content here. So I'm going to close the window, and now it is time. In other words, I'm done specifying the definition of a subroutine. Now we have to go back to the RAM content and make use of that. Okay, we have a second instruction to implement, just so that this is more realistic as a homework assignment. So this is the next one. This is specifying 7. Okay, this is in binary. I put question marks here because these bits really do not matter because this particular instruction, actually, I take it back. These 2 matter because it is a jump instruction. Or I call it skip. It's a jump, go to, whatever you want to call that. So what this will do is it will use whatever register you specify here to specify where we are going to continue execution in RAM.
Dereference? So it's like an indirect,
It's kind of like an indirect go-to, so to speak, because you're using a register to specify where we are going instead of stating exactly where we are going in the next byte.
So the register is going to hold a RAM address.
Correct. The register is going to store a RAM address, and then we are continuing execution at that particular RAM address. So the instruction simply skips the PC, the program counter, to the address stored in reg in this case. And to do this, we have to examine the processor design and find out how the program counter can be updated by the register bank. So we go back to the design, and then we start with the program counter in this case. So you can see that it is really important that you know your way around the processor architecture. And we look at the input, we look at the program counter. This is the program counter. We look at the input into the register, which is this line here. It goes into a mux, okay, which means I can choose one or the other way. And one way is going to this line here, and you can see this line goes all the way into the register bank so that we can use register output 0 to connect to the program counter. So what you need to do is to write on the side, use a notepad or something to write this down. So we can basically establish a path from register out 0 going through the mux. But when you go through a mux, you have to specify, okay, but what value of the mux do we need in this case? So if you scroll down a little bit, and we want this one, so it is a 0 in the mux, okay? So the selection into the mux is going to be a bit 0 because this mux only has two input and 1 output, so 1 bit is enough to specify that. And then from the mux, it goes into the program counter. Since we want to change the program counter, you also have to know, which bits of the program counter we need to exercise in order to get this done. And there are 2 bits involved in every single case when you have to do something about a register. The first one is the enable bit, and the second one is the clock. The clock is not something that you can specify, so forget about specifying the clock, but you do have to put a 1 into the enable in order for the program counter to be ready to be changed. Are we still doing okay so far with this little chain here? Okay, all right. So now that we have this part here, we can now go to the microcode and specify all the 0s and 1s. So once again, we go to the spreadsheet and we reset all the way back to here. This is instruction number 7 in hexadecimal, and this is our skip instruction, or if you prefer jump is fine, okay? So we want to skip to a particular register, and that register has to be register 0, okay? The ALU output, it really does not matter what we specify here because it doesn't do anything. MCC clear has to be a 0. Register 1 output enable is going to be a 0 because we're not doing anything with register 1 output from the register bank. But this one has to be a 1 because we are using it. This one has to be a 0 because we are not changing any one of the registers in the register bank itself. Indirect register is not being affected by this instruction. Put a 0 here. We are not dealing with RAM at all. Put a 0 into RAM selection. We are not doing anything with the microcode itself, so we want it to keep incrementing, which means we have to select a 0 here. RAM address PC /indir is, we are still using the PC, the program counter. It's not really being used at this point, but putting a 0, putting a 1 here is kind of the default. Bit 11 is not used. We are not writing or reading to RAM, so if you have to specify 1, just be safe and specify a read operation. We're not using the ALU, so ALU output enable is a 0. We are not changing the instruction register itself. It's very seldom that you have to change the instruction register itself. If anything, it's going to be in the fetch cycle. Okay, there should be almost no other case where you have to do this. Okay. So we'll put a 0 here. We're not changing the instruction register. We are not changing. We are going to change the program counter register. So we'll put a 1 here to enable writing or overwriting the program counter. And this is the important part. Okay, are we specifying? How are we specifying the input into the program counter? And we are now selecting 0 instead of 1 because we don't want the program counter to just increment. We want to basically use the other way of the mux to specify the new content of the program counter, and that's it. So once we specify all the bits, we copy and paste the number that is representing those operations, and this is the first time we end up with a number that is not starting, that has less than 5 digits. So what you need to do is to pad zeros on the left-hand side, not the right-hand side, okay? Because this number is 9420, but it's also 09420. So we want to make sure that that is entered into the ROM. So it's 9420 into page 7. Yep.
You don't have to type the leading zeros. It just assumes it.
Okay. So we switch back to here, and then we go to the ROM. And you can keep this window up if you want to. I just close it because I don't, I don't want to switch to this window unless I need to. So 09410, I think. And this is page 7 because the most significant bit of the instruction is 0111. Okay, so we are now ready for the next instruction or the next microcode. And if you go back to the spreadsheet, the next microcode can be just the same as all of the other ones because we are ready to go to the next instruction cycle. Yes?
You wrote down 09410, it's 09420.
Sorry?
It's 09420, but you wrote down 09410.
Oh, okay. 9420. So I wrote down the wrong number. 9420. Oh, yep. 9420. There we go. Thank you. All right. So the next instruction, can be the same as all of the other ones, but we'll kind of go through all the bits just to be sure. Okay. So we're gonna say, the ALU operation really doesn't matter. You'll pick whatever you want to pick here. MCC clear. This is the important one. We want that to be a 1, and everything else should be turned off. Okay. So we'll go ahead and turn off this one. Turn off this one, turn off, turn off, turn off. This one, the MCC load. Yeah, this one, can be anything because we're resetting it anyway, so it doesn't matter what it is they're specifying here. The RAM address thing will continue to specify 1 to come from the PC. The fetch instruction, the fetch cycle is going to take care of that also, so we really don't need to specify one way or another. So we'll just kind of copy, most of the other stuff here. Instruction register write, turn to 0 here. PC write enable. Now we can put it back into a 0 because it would have experienced a clock cycle already to clock in the new content into the program counter at this point. Okay. Let's see. We'll keep moving. And then any question?
We just talk about that PC right. Enable if it's 1, then we are rewriting there, refresh new value. If it's 0, keep the old value.
Okay, so to answer your question, why we put a 1 here or when we put a 1 here, you have to go into the design here, and then you identify what is a program counter. The program counter is a register. So if you want to, go all the way to the source documentation, I would go to the library reference, go to memory library, go to register, and study this. That's what you need to do in order to understand how the architecture works. Okay. Yeah, this is one of those homework assignments, or not one of those. This is definitely a homework assignment where you don't want to just kind of make random changes to the bits and hope that one of those changes will work. Yeah, fuzzing is not going to work in this case.
No fuzzy logic?
Yeah, fuzzing will end up with, probably some really bad results.
Fuzzy
Yep. Okay, so getting back to here. Now the documentation of Logit Sim, I think I have said this many times already, is exceptionally good. Okay, for a free, open source program that has not been updated for the past 2 years almost. This is actually a really, really nice package. Most of the instructions here or the description here is really, it does work. I mean, it works. It works for me. If you read this instruction and you still have a question about it, let me know and I can write something to clarify that. Okay. But the first thing is to read this part here.
And you got there. You got to that the documentation portion. How?
Oh, there you go.
Help.
Yeah, just help. But you want to go to the library reference. Okay. The other parts can tell you how to use the tool, but the library reference is where they define each and every single component and tell you how to use it.
Plus, you also have a new document.
Sorry?
You also have a new document that
Yes,
consolidates all of it.
Yep. But it's a little on the terse side because the actual full definition is in the reference manual already. Okay, so now we can go back to the ROM here and specify the next microcode and go back to the spreadsheet to figure out, oh, we're not done. We have one more thing to do. We can now switch this back to RAM data if you want to. It doesn't really mean an increment. So we can now specify a 1 here. Okay. Now this first being a specifying increment is not going to affect the actual fetch cycle because the fetch cycle will grab the content at the current location first, and then it will increment the program counter. So that's why, you know, even if I put a 1 here, it's not going to affect the fetch cycle. Okay, let me just kind of show you what I mean by that, because I'm pretty sure some people have that question. It's like, but isn't that going to mess up the program counter, because it will just be incrementing itself? It won't be incrementing itself because the write enable is already turned off. So even though we specify, hey, you know, grab the content from the adder, it's not going to do a single thing. So now getting back to the spreadsheet, now that we have all the bits specified, we just copy and paste those 2 cells, and you can see 11408 is once again, you know, the bit pattern here. So it's basically a typical ending for an instruction, where, you know, okay, everything is done, just reset the microcode counter to the beginning, and we're all good to go. So going back to the ROM here, we specify the same thing, which is 11408, and that's the other instruction. So now I have defined 2 new instructions, or the microcode of the 2 new instructions, but the program is empty. There's no program to make use of any instructions at this point, because, okay, once again, before we move on any further, save it. There we go. And the reason why there's nothing to run, nothing to program, nothing to run at this point is the RAM content is empty. Well, it's not empty, but it's not specified. Okay, so now we need to specify the actual program to go into RAM in order to do something, you know, with the opcode that we have just defined. In other words, it is equivalent to defining 2 new subroutines or new functions in C and C++, but there's no call yet from main to, or anywhere, to these 2 new subroutines. Okay, and that's what we're going to do next, is to, you know, specify quote-unquote the call to those subroutines in RAM. Okay, so switching back to my description here, and it says you're strongly recommended to save this file solution.rom as frequently, so that if the program does crash, you won't be losing a lot of work, blah, 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 blah. And now we want to implement a small program in RAM, and save it as solution.ram, and it's going to be as follows. And you can see that this is almost the same format as your homework assignment, except this one is a little bit simpler, but not really that much simpler. Okay, it's just different instructions. So we want to use RAM location 00 and 01 to write an instruction to load a particular constant, D5 in this case, into register C. So how do we specify such an instruction? Okay, several things. First thing is to go back to the spreadsheet and figure out what is the opcode, the most significant 4 bits of the instruction that can load a constant into a register. So if you look at row 8 of the spreadsheet, that tells you, okay? It's the load instruction, and it's the most significant 4 bits should be 0001, and the register that is being changed can only be this one here. So you can put any bits you want, you know, here, but this one has to specify the register that we want to change. So, but the instruction of the homework assignment specifies which one we want to do. We want to use is register C. 00 specifies register A, 01 specifies register B, so that means 10 specifies register C. We doing okay so far? So this instruction can now be known in RAM in hexadecimal as 1, 2, right? Because, you know, if you put 00 here, it is 2. But you can put any bit patterns here, it will just be ignored. So this is also known as 1, 6, okay? Because if you put a 1 here, it becomes a 6 here. It is also known as 1A. If you put a 1 over here and a 0 over here, that is 10, which is A. It is also known as 1C, which is 1E, which is 1110. Okay? So all of these are acceptable because, you know, we don't really care about bit 2 and bit 3 of this instruction. Are we doing okay so far? Okay. All right. So I'm just going to take the first one, you know, just, you know, putting zeros into the bit positions that are not used. So now we go back into this part here, change the RAM content, and we specify the instruction, which is 1, 2. And then the next byte is also used because the load immediate into a register instruction takes up 2 bytes. The first byte is the actual instruction, The second byte specifies the value that you need to store into a register. So in this case, I believe it is D5. So you put D5 here. Are we doing okay so far with this program, the first instruction?
That
Okay.
2 is 1 0.
Huh?
2 means 1 0, is that right?
2 means,
From 0 1 0.
yes, these are bits, individual bits.
How you get 7, the first part 0001, so that's in instructions?
It's from the spreadsheet. The spreadsheet says, this is the hexadecimal digit to go into the most significant 4 bits.
Gotcha.
Yep. Okay. Any other questions? It's all good so far? Okay. So the next step I have to implement would be something about the same. I'm using the next 2 locations to write an instruction to load 77 into register B. So I'm not even going to go through all this calculation here because it is very similar to the previous instruction. So we want to load into register B, which means the instruction itself is 1 1 because B is 1 less than C. And then the constant, of course I cannot remember that, is 77. Okay, so we put a 77 into the next byte. And once again, it's a good idea to save this often, so I'll save it as my solution.ram. Okay, now you have to remember not to overwrite the wrong file, okay, because you definitely don't want to do that. So click save here. And now we are moving on to location 4. So on location 4, we want to write an instruction to compare register B to C, and I specify here we want to subtract C from B. Okay, and we still have it here. So the subtraction goes like this, which is register out 0 minus register out 1. So we want register out 0 to specify register B in this case, and we want register 1 to specify register C. Okay, so when I refer to register 0 versus register 1, I'm referring to the output of the entire register bank. When I refer to register A, B, C, and D, I'm referring to the individual register inside the register bank. Okay, is that okay? Okay. So we'll keep this one up and look at the instruction here. Okay, so we want to do a subtraction, and that's the most significant hexadecimal digit is going to be a 6 because that instruction starts with 0 1 1 0, which I had earlier on the whiteboard. Did I put it on the whiteboard? For the compare.
Yeah, well, yeah.
Did I? Okay. So a 6 as the most significant digit. So the least significant digit in hexadecimal is the most important one because we have to get the direction right. So we want, according to the instruction in the assignment description, we want B to be register 0. So that would make it a 0 1 in binary. We want register 1 to be a C, which means that is a 1 0. So combining those two, we will be specifying 1 0 0 1 as the least significant 4 bits. So that would be a 9 because it's A plus 1. So 6 9 is the instruction to compare register B to register C. Is that okay? Sort of? Okay.
Can you say that one more time, please?
You guys have no idea how difficult it is for me to say something again because it's not stored anywhere here. It's kind of like the ALU. It doesn't store anything. Okay.
That's what the video's for.
Yeah.
Exactly. That's why the video has the audio as well, right? Okay. So we want this to be register B. We want this to be register C for this specific instruction. Is that okay? Okay. Register B is a 0 1 because register A is 0 0, and this is 1 0. But this is actually bit 2 to bit 3. This is bit 0 to bit 1 of the instruction itself. So when you combine this is 1 0, this is 0 1. So these 4 bits become the least significant bits. Is that okay?
Oh, I would get that.
Yeah, you have to look at the instruction, in basically chunks of bits because different chunks of an instruction serves a different purpose. Okay. All right, so we are done with the compare instruction, and the next instruction taking up location 5 and 6 is loading 10 and in hexadecimal into register 8. So I already know the instruction, which is a 10 because the 1 in hexadecimal specifies a load immediate instruction, and then the 0 specifies register 8. And then the next byte specifies the constant that we want to use to overwrite register A, which is also 10, okay? So that's why the instruction itself is 1010, but the two 10s have different meanings. The first one is the instruction, the second one is the actual value that we want to use to overwrite register A. So we kind of still doing okay? There's no easy way for me to change this. I wish I could maximize the font, but I don't think I can change the font size. Nope, doesn't look like it. Okay, so now we have this instruction also specified, and then I said at location 07, write an instruction to skip and continue execution at the address stored in register A. That would be the new instruction that we have been implementing, starting with a 7 as the most significant hexadecimal digit. And since we're using register A, the least significant 4 bits will be 0000. So 70 is basically saying, okay, we'll use a jump instruction, but we'll jump to the location that register A is pointing to, because register A is more or less, acting as a pointer in this case, because it stores an address. Are we still doing okay so far? Because this is the workflow of the homework assignment. Okay, you kind of have to go between all of those different components in order to get it done. The next one is here. It says at RAM location 8, which is where I am at this point, write an instruction that is not implemented. Okay, so F0 will be an instruction that is not implemented, right? Because we have only implemented 0, which is the fetch cycle. It's not actually an instruction. We implemented 1 and 2. One is a load immediate instruction. The other one is store indirect. And then I skip all the way to 6 and 7 because the other 3 instructions are the ones that you have to specify. Okay, so we are slowly building up the repertoire of this particular processor. Okay, but some instructions cannot be done yet because I don't have the pathways within the processor yet. This instruction, this location is not used. In fact, we are not using anything until we get to 10 in hexadecimal. This is the part where when you replay this in YouTube, it looks better because you can actually maximize the window and actually see all the numbers and where the cursor is and stuff like that. But at location 10 and location 11, we will overwrite register A with a constant of FF just to signify that we got here. Okay, that's all it's intended for. So here we specify 10 as a load immediate into register A instruction, and then the next location specifies the constant that we want to use to overwrite register A. So that would be FF in this case. So that concludes this particular homework assignment. I have not done a single test of anything yet. So now would be a good time to test this whole thing and see whether it works or not. But as far as the development part is concerned, are there any questions about the workflow of what I just did? Questions? Yep, go ahead.
When you did the skip, where did that 0 come from? When you did the set, where did 0 come from again?
Because I am going to use register 0 to specify where I'm going to continue execution, so that's where the 0 is coming from. If I use register B, then it will be 1. So it'll be 7-1 as an instruction. If I want to use register C, it'll be 7-2, and then 7-3 will specify register D as the register containing the address of where I'm supposed to go. Yep. Say again? Yeah. 8. Just to make sure that I'm not going to execute it.
Awesome.
Because if I ever execute at red location 8, something is not right. The skip instruction is not working. Yeah. Because I just want to put something there so that it's it would signify, it would tell me that something is wrong. All right, so it's time to test this code, and for better or for worse, okay, I have not tested the microcode nor the program itself. I just came up with this stuff along the way. So I'm doing this as a homework assignment the first time, just like you guys are doing your homework assignment. Which is good in a way because, well, okay, let's talk about the bad part first. Because the bad part seems like, hey, Tech is not preparing for his class. But he's not preparing for his class for a reason. Because I want to go through the same process that you guys have to go through. If I prepare everything ahead of time, I can just give you the 2 files. Like, okay, I'm done with this homework assignment, learn how to do it. That would not illustrate the workflow, nor any error that I may encounter. Because if I have an error here, it's actually a good thing. Because then you can tell, okay, but how do we debug the microcode? What if something is not working the way it's supposed to? Okay, but even if this code is perfect, which I really doubt, I can still show you how to test your program step by step to make sure that it does work the way it's supposed to. Okay, so before we do anything else, definitely remember to save the file again, okay? Because if Logisim decides to crash at any time, you don't want to lose the program that you have entered at this point. All right, so we'll go to Logisim and we'll actually do some execution. We'll start execution at the first location. All right, so the execution is done by the clock signal here, and some of you can change this clock to make use of the actual clock signal. And I'll go ahead and do that just so that you can see what it is and the advantages of doing that. So I'm changing the architecture just a little bit, okay? Not a whole lot. If you don't feel comfortable doing this step here, don't do it, okay? It's not necessary. You know what? I'm not going to do it. The reason why I'm not going to do it is because the transition both ways is actually significant, so I'm not going to do it. All right, so we are now ready to do everything, and since I have already severed the connection from the reset line, which is, the pin is all the way up there. Right there. Okay. So we're going to reset the whole thing, but since the RAM is now disconnected from the reset line or the reset pin, it's not going to reset the content in RAM, which is good because everything, otherwise I will have to reload everything from the file. Okay, and now we are ready to go. Okay, so we'll go ahead and start with the execution, and we'll just have to clock this line here. So 1 clock, and you can see the change is it's just going through the microcode here, not much else. Okay. Clock again, and moves on to the next instruction or the next microcode. This is the one that will decode whatever is in the instruction register. So this is a good time to check the instruction register and see that the first instruction, which is 1, 2, is already loaded into the instruction register. The next one will continue execution at location 10 in ROM because it is where the microcode of the load immediate instruction is located. So I'm going to clock it. And sure enough, we are now at location 10 of the microcode portion. And this instruction is already implemented. I'm pretty sure it does work correctly. So I'll just kind of do this relatively quickly until it gets back into the fetch cycle. But the side effect of the first instruction is something should be in register A already. No, I take it back, register C in this case. So it would be a good thing to double check, okay? When you're writing your code, it is also something that you want to do. And this time you do want to switch to the hierarchical view of the simulator because this will allow you to look at the current state of the registers. And you just need to double click on the register bank, and you can see register C is in fact loaded with the constant D5, which means the program is working correctly, at least up to this point. So we go back to the main circuit here, and we'll go ahead and execute the next load immediate instruction. And we can do that by just clocking it a few times. Okay. Now we are ready to decode, continue execution at location 10. And now we're going back to the fetch cycle. So at this point, register B should be 77. So once again, I go to the register bank and check that register B in fact has a content of 77 in hexadecimal at this point. Okay. Are we still doing okay so far with the execution of the program that is stored in RAM. Okay. All right. So the next instruction is the new one because that's the compare instruction, right? So now we switch back to the main and clock it again. You guys don't have to scroll as much as I do because I'm hopeful that hopefully you guys can fit everything onto the screen, so you don't have to scroll as much as I do. So now we get the next instruction. Now we decode the next instruction, which is the compare instruction, and now we continue execution in the ROM at location 60, okay, which is what it is expected to do, because the compare instruction starts with the 6, and we are using that to specify where to go in the microcode ROM to continue the microcode decoding. And this is the instruction. This is the microcode that will actually do everything that we need in order to do the calculation in the ALU. So we'll clock it. And this is darn it. Yeah, we did it. I did it a little too quickly. Okay, so let's see if I can still check whether the microcode, the ALU has the content that I want. Sorry?
Just replay back your video.
No, I cannot because I have to inspect the ALU, when the clock cycle, because I, yeah.
To start over from the beginning. To start over from the beginning.
I don't need to go all the way from the beginning because I can doctor it. Okay, so you remember, going through this process is good because I just, did something that I'm not supposed to. So how do you restart the program from a certain point? Change the, which register is in charge of the program counter, the PC, okay? The program counter. The microcode counter is already back to 0, so that's okay. That we have done already. So we just have to go back to the description here and say, okay, this instruction, the compare instruction, went a little bit too fast. Okay, so we'll go back to this one and say, we want to go back to location 4, which means we're going to doctor the program counter to 04. All right, so the program counter is down here, and we're going to change this to 04, and now we are back to location 04. And you do have to make sure that we are starting from the beginning of the fetch cycle, which it is. So now we'll go through this whole thing again. Continue onto 60. Do the rising clock and stop. Okay. Because this is where it is going to change the state inside the ALU. So we go to the ALU.
This is the compare instruction, right?
This is for the compare instruction. So we are now, specifying a whole bunch of stuff. You can see that we are subtracting D5 from 7, and that's the way it's supposed to work. What is the result? Are we outputting the right content? Is this the right thing? So this would be a good time for you to kind of brush up your binary subtraction thing. Yep. Yeah, let's do it. Let's do it. This is fun. Minus D5, right?
Okay, cool.
Let's do it in binary. So the other one is what, D5? So D5 is a 1, 1, 0, 1.
No, you were saying we were. It's quicker.
Yeah, 1 hexadecimal digit is 4 bits. So we'll do the subtraction here. We'll put a 0 here, and then we do the full subtraction thing. 1 minus 1 is a 0. 0 minus 0 is a 0 with no borrow. I'm just running the full right up here. Yeah, the whole experience. Well, I skipped one column. Okay. So it's 1 minus 1 is a 0. 0 minus 0 is a 0 with no borrow. Okay. So far so good. Okay, so far so good. And then we check this one. 1 minus 1 is 0. 0 minus 0 is a 0 with no borrow. That's going to be a 0 here, no borrow. 0 minus 1 is 1, 1 with a borrow. 1 minus 0 is a 1. Okay, so far so good, because the output of the ALU is in fact the difference between those two, and we have a borrow of this extra one as C out. So everything does work as expected, okay? Yep, go ahead.
In the full implementation, that would be telling us, that borrow would tell us our compare. That would be the actual value.
That is correct. But at this point, it is not stored anywhere within the process architecture. Okay, so that's something that we will expand later on.
That's the two? That's the Microcode 2, 3?
Yeah. We'll talk about it when we get to the flag discussion of the class. So what we'll do is we'll talk about what the flags are, why they are there, and then we go back to this architecture and say, okay, now how do we implement all those flags? There are 4 of them. There's the Z flag for 0, the carry flag itself, there's an overflow flag, overflow, which is not what you think it does. Okay, so the overflow flag is not the carry flag itself. And there's one more, which is the sign flag. Okay, so we'll implement all of those flags when it's time. Okay, so we are almost done with the simulation. So we'll go back to the main design here and start clocking again. Okay, so we clock back to the first one. Okay, so I just ran the compare instruction. Now we want to put 1, 0 into register A and then do the skip instruction. Okay, so let's go ahead and do that. Okay, this is the load instruction, which is something that we have done many times already, and we are not too concerned about it. The only thing we might want to do is to go to the register bank and just double check and make sure that register A is now 1, 0. Okay, so we look at that, and register A is in fact 1, 0 at this time. So that instruction worked okay. Go back to main, and now it's time to do the skip instruction. Now this is something new, so I should do it slowly, right? Okay, so we have load instruction, put it into the instruction register and decode it. And this time we start execution at 70 in ROM, which is correct, okay? And this is going to put it into the PC. Okay, so I'm going to do the clock up, and at this point PC should be changed already, because a rising clock to all registers except for 1 is going to perform the actual write operation. Okay, the only register that is clocking on the falling clock is the microcode counter itself, and that's done for a reason, because it needs to be off from the rest of the clock cycles. Okay, so we want to look at the program counter, and the program counter is in fact 1, 0. If the instruction did not work, what would be the value of this one? It should be 0, 8. Yeah. So this is already telling me that the instruction is in fact working. But we can also continue to clock it and go back to the fetch cycle. Now when we're in the fetch cycle, when you look at which RAM is selected, that tells you which instruction we're about to load into the instruction register. And it is in fact going to location 1, 0. And now this is kind of confusing, because we are at location 1, 0, and the instruction at location 1, 0 is also 1, 0. But those two, it's completely coincidental. Okay, that is completely coincidental. One specifies the location of the instruction, which is the 1, 0 outside of the square or the rectangle, and then the 1, 0 that is being highlighted is the actual content at that location, and we just turned out to have the same bit pattern, which is the address and also the content at that location. But this 1, 0 specifies load immediate into register A, and the FF next to it is the constant that we're going to use to overwrite register A. So when we clock through this instruction here, this is load, this is decode, and now we execute the load instruction itself. When we go back to location 0, we should have FF in register A. So we'll go to the register bank and just double click this one and see that register A in fact has FF in its content. So that's the whole process to kind of do the homework assignment. You start off with the implementation of the microcode first. Do it one at a time. You can actually try to debug those things individually. So you write a microcode, and then you specify the content in RAM, which are the actual instructions, and then you clock through the Logit sim to see the instruction execute, and then you have to examine the various parts of the architecture just to make sure the instruction does what it is supposed to do. Okay. Yep.
We need to keep the register value there, like B and C. We running from last instruction. Do we need to keep the value there?
Keep what value where?
Register B and C.
Register
Now we
B and
can-
register C?
Yeah, now we use A.
Well, the program should not change register B or register C because I did not specify any instruction to change those. So if for whatever reason your program is changing registers when it's not supposed to, it will still be a wrong implementation.
So we don't need to clean this data.
Sorry?
We don't need to clean this register B and C. We keep the value.
Because the registers will keep its content until you tell it to change or to reset to clear.
Yeah, so for our homework, we don't need to clean.
We don't need to
keep
what?
It. We keep it. We keep the value.
You keep it the way it's supposed to be. So the side effect of each instruction to change the registers is the way it is. I mean, you don't. Your program has to do what the instruction is supposed to do. That's basically the bottom line. Hmm? Why do you want to change it to 0, 0?
If we don't want to keep the value, I just wonder why do we need to keep there? Because now that doesn't work.
But your program does not specify anything about clearing those values,
yeah,
right?
We did, yeah, because we put 0 there, so it didn't keep, it's just keep the value there.
I still don't understand the concern.
Because you save all the data in the RAM location, until you specify to delete the data, it's still there.
Yeah. So we, okay, we'll keep
I don't understand the concern
yeah, we'll
because,
keep it there.
okay, now here comes the second part. We are running out of time. We have 2 minutes left, 1 minute and a half or so. Okay, so this is the part and say, okay, suppose you made changes to the microcode, because you figure out, oh, okay, I forgot to do this and whatnot. So how do we run the program again? You have several options. Okay, now that I have severed the connection from the reset line, I can actually do a full reset and not really have to worry about anything in RAM. But all the registers are now reset. Okay, so you have to keep that in mind. Is the reset line is still going into the register bank, so registers A, B, C, D will now all be zeros. So that means you can't really just doctor the program to start running at a certain location unless that instruction does not depend on existing values of the registers. Okay. Now, if you do want to save the entire state and actually do stuff like that, you can kind of do that because even the registers in the register bank here can be doctored. You can change this one to FF, change the next one back to whatever we want it to be, 77, DF, D5, and whatnot. So now you can actually restore the values in the registers. And once you are done with this step here, you can now go to main and then doctor PC, the program counter, to a certain location. And I think it was 0, 5, 0, 4. I cannot remember. Okay, go back into my
04.
0, 4. Okay, so let's put this into 0, 4. And so you can basically now start execution at location 0, 4 again without executing the first few instructions first. So that can potentially save you time because now you don't have to rerun the simulator from all the way from the beginning. And you can start at a certain location. But it does depend on the fact that you have to restore the content of the registers as well in order for the side effect of the instructions to be the same. Is that okay so far? Because this is a really useful tool because if you have implemented most of the instruction and tested most of them correctly, it's just the last one that is not working correctly. This will save you a lot of time because you just reset to this location and just start from here. Any other questions? Okay, one more time, before you're done with this and you walk away, just make sure that you save, the file content, okay? Because that is really important. Once you set up the file correctly the first time, it will keep the same name, so you don't have to worry about saving into the wrong file after the first time, okay? And there will be 2 files that you have to upload. Both the RAM file and the ROM file need to be uploaded into Moodle, and it has to be solution lowercase .ram or solution .rom. All right. Okay. If there are any questions, I will answer those questions in the lab. Okay? And we'll take a 10-minute break. I'll see some of you over at the lab. The homework is not due midnight on Thursday because that's not what you want, okay? It's due at 7 p.m. on Thursday, right before the class.
That would have been my one question to ask.
Yep, I can read your mind, and I forgot to take roll again.
I said it in their mouth.
Jeez.
Yeah, you know what?